Okay, so we are looking at an application of derivatives where we are trying to minimize the surface area of an object. And so in this example, we have a canvas wind shelter for the beach. It has a back, 2 square sides, and a top. And we want to find the dimensions for which the volume will be 250 cubic feet. That requires the least possible amount of canvas. Okay? And so since we're talking about minimizing a quantity, we know we have certain constraints that we're working with, and then we have certain objectives. So we are constrained by the volume, right? So the volume is 250 cubic feet. Again, that is our constraint. Okay, and then we have an objective, right? Our objective is to find the least possible amount of canvas. Right, so the least possible amount of canvas is going to be our objective. Okay, and so we use this then to guide us as we set the problem up. So let's go ahead then and represent our constraint equation and our objective equation. So for our constraint, okay, we are constrained by the volume. So that's simply length times width times height. So by our diagram, we have the length and the width and the height given by x, and y. The volume is given to be 250. And so 250 equals x squared y. Okay, we're going to have to solve that for one of the variables to perform our substitution. So y equals 250 divided by x squared. Okay, and now we're going to write our objective equation. Okay, so our objective, again, is to minimize surface area. So we know our objective equation is going to involve surface area. And so we have then 4 surfaces, essentially. We have an x by x, we have another x by x, and then we have 2 xy's, right, if you were to look at all sides of that shelter. So our surface area could then be represented by 2xx, right, or 2x squared if you prefer, and then 2xy. Okay, so we have 2x squared plus 2xy. All right, and so now we're going to rewrite this objective equation by substituting in for y. So this quantity right here, we're going to sub in for y in our objective equation. And so doing that, we then have our surface area equal to 2x squared plus 2x times, let's see, 250 all over x squared. Yep, there we go. And then we simplify. Okay, so we have our surface area equals 2x squared plus 500 all over x. Okay, and then we are going to find the minimum by taking the first derivative. Okay, so with the first derivative, we're going to here find that that is 4x minus 500 all over x squared. We set that equal to 0, so 0 equals 4x minus 500 divided by x squared. Okay, and so then we solve, so multiplying through by x squared, that yields 0 equals 4x cubed minus 500, which then gives us x cubed to be 125. So x is 5. Okay? So therefore, we need our x to be 5 feet, and we can find y by plugging back into our original equation that we have for our constraint. And so we have x to be 5 feet, and we'll plug 5 in to find y. And so plugging that 5 in, we'll get y to be 10.